I want you to picture a scenario that I think is universally painful.
Okay.
You brew the absolute perfect cup of coffee. It is steaming. It is aromatic. It is the only thing standing between you and a total mental breakdown.
I'm with you so far.
You take one phone call, maybe answer two emails. You reach for the mug, and it is stone cold.
Thermodynamics. The ultimate killjoy. Heat always wants to escape.
It is the tragedy of my mornings. But it got me thinking about how we handle heat in general. I mean, we've gotten really good at turning sunlight into electricity, right?
Sure, solar panels are everywhere.
But storing the sun's heat, that feels like we are, I don't know, still in the Stone Age.
It's a fair point. We usually store energy as electricity in batteries, like the lithium-ion ones in your phone or an electric car.
Right.
But batteries leak charge over time, and fundamentally, they don't store heat. They store electrical potential. If you want to keep something hot, you usually have to, burn something or use a ton of electricity to generate that heat from scratch.
Exactly. But what if I told you that we could literally bottle a star?
Bottle a star.
I'm talking full Harry Potter, liquid luck, file of Galadriel stuff, a liquid that sits on your shelf holding on to the energy of the sun for years and then snap boils water on command.
It sounds like fantasy or maybe alchemy, but as of last week, it's very much reality.
Welcome to the Deep Dive Lab. Today, we are unpacking a paper published just last week in Science that honestly just blew my mind.
It comes from a team at UC Santa Barbara and UCLA, led by researchers Grace Hahn and Ken Hook, along with the lead author Han P.Q. Nguyen.
And the title of the paper is a bit of a mouthful.
It is. It's Molecular Solar Thermal Energy Storage in Dewar pyrimidone beyond 1.6 mJ/kg.
Catchy. I'm sure the movie rights are already sold. But despite the dense title, what they've done is create what I can only describe as a molecular mousetrap. They have found a way to hack the code of sunlight storage, and the weirdest part, they stole the idea from skin cancer.
That is a dramatic way to put it, but you're not wrong. It's accurate.
Yeah. So let's dive in. What exactly is our mission today?
Our mission is to understand how this team engineered a molecule that beats the best batteries at their own game, how it turns water into a thermal battery, and why this might be the end of scraping ice off your windshield forever.
Okay, but before we get to the cancer-inspired molecules, I need you to clear something up for me. I've used those little hand warmers before.
The ones with the metal disc you click.
Yeah, you click it and the liquid turns solid and gets hot. Is this the same thing?
That is a great question, and the answer is no. None at all, actually. Those hand warmers use what we call phase change materials.
Phase change.
They work by freezing a liquid into a solid, which releases heat. It's like how water releases heat when it turns to ice instead of, a much higher temperature.
Okay, so that's physical, liquid to solid.
Right. But this new research is about chemical storage. It's called MOST, Molecular Solar Thermal Energy Storage. We aren't just changing the state of matter. We are changing the actual identity of the molecule itself. We are forcing it to hold energy in its bonds like a coiled spring.
So the hand warmer is like letting a hot rock cool down, but this is like winding up a jack-in-the-box and then closing the lid.
That's a perfect analogy.
Right.
Exactly. And because it's chemical, the energy density, the amount of power you can pack into a small space, is on a totally different level.
Okay, I'm with you. Now, let's talk about that inspiration. You said this comes from nature, but not the nice part of nature.
Right. Normally, when we look to nature for solar inspiration, we look at photosynthesis, how plants eat sunlight to grow. But Grace Hahn and her team looked at damage. Specifically, what happens to your DNA when you get a sunburn?
Okay, so I go to the beach, I forget my sunscreen, I turn into a lobster. What's happening on a molecular level?
When high-energy UV light from the sun hits your skin, it slams into your DNA. Your DNA is like a twisted ladder, right?
The double helix.
And the rungs of that ladder are made of nucleobases. When UV light hits a specific type of rung called pyrimidone, it causes a violent reaction.
It breaks the ladder.
It actually twists it. It forces the molecule to snap into a new knotted shape. In dermatology, this is called a 6-4 lesion.
A lesion. That sounds bad.
Oh, it is. It's a mutation. It kinks the ladder so your DNA can't replicate correctly, which is often the starting point for skin cancer.
So nature figured out a way to trap the sun's energy in a chemical bond, but it uses that power to give us tumors.
Precisely. The energy from that UV photon isn't lost. It gets stored in that strained, knotted shape. The researchers looked at this and thought, that is terrible for skin, but it is a brilliant mechanism for a battery.
They saw a bug and called it a feature.
Exactly. They wanted to harness that shape-shifting ability. The idea is to have a molecule that has two shapes. State 1 is relaxed,
Like me on a Sunday.
like you on a Sunday. Low energy, just chilling out. Then sunlight hits it. That's the input. The molecule absorbs that energy and snaps into state 2,
The mousetrap.
the mousetrap, or as the paper calls it, the Dewar isomer.
Dewar. Why Dewar? Is that named after a person?
It is. It's named after James Dewar, a Scottish chemist from the late 1800s. He theorized a specific structure of benzene that looked like two squares folded like a book. This molecule forms a similar cage shape,
So it's a strained structure.
very strained. It wants to pop back open, but it's locked.
And unlike a battery, which is always, slowly leaking electrons, a mechanical spring doesn't leak, right? If I set a mousetrap and put it in a box, it's still ready to snap 3 years later.
That is the magic of it. And that's what makes this different from any solar panel. A solar panel gives you electricity now. If you don't use it, it's gone. This molecule is the storage. You catch the sunlight, the liquid changes shape, and then you can put that liquid in a tank, a barrel, or a bottle, and it just sits there.
Waiting for the trigger. And how long can it wait?
In this new paper, they found the half-life of the charged molecule is up to 3 years.
3 years.
You can leave a jar of this charged liquid on a shelf, come back in 2029, and the energy is still locked inside, ready to go.
Okay, hold on. I have to play devil's advocate here. I mean, the concept of these shape-shifting molecules, it isn't brand new, right? I feel like I've heard of solar fuels before. Why is this paper in Science? What did they do that's so different? Why haven't we solved this before?
You are right to be skeptical. Scientists have been trying this with other materials for a while, things with impossible names like norbornadines or isobarenines.
I'm not even going to try to pronounce those.
Please don't. The problem with those older candidates was usually a kind of Goldilocks issue. One, they didn't store enough energy. They were weak springs.
Okay.
And two, they were incredibly toxic.
Toxic how?
Like, can only be dissolved in benzene or toluene toxic.
Uh-uh.
These are nasty, carcinogenic organic solvents. You do not want 500 gallons of benzene circulating through the pipes of your family home.
Definitely not. So the previous tech was either too weak or too dangerous.
Or just too expensive to make. The breakthrough here is that the team engineered a specific derivative of that DNA molecule, specifically 1,004 pounds and 56 trimethyl-2-pyrimidone.
Let's just call it the solar pyrimidone.
That works. And the headline feature of this solar pyrimidone is that it is water-soluble.
That sounds simple. Just add water, but in chemistry, that's a big deal.
It's a massive game changer. Organic molecules usually hate water. But by adding these specific methyl groups, the researchers made it dissolve. Water is safe, water is cheap, and water has great thermal properties. Being able to dissolve this sun-catching powder into plain water means you can pump it, store it, and use it in existing heating systems safely.
Okay, so it's safe, it's cheap, and it flows like water. But does it pack a punch? Because if I have to fill my entire basement with this stuff just to heat a cup of tea, I'm out.
This is where the numbers get wild. We measure energy density in megajoules per kilogram.
MJ per kilogram. Okay, hit me with the comparison.
A standard lithium-ion battery, the gold standard of modern storage, the thing in your phone and your Tesla, holds about 0.9 MJ kilori.
Okay, 0.9.
This new liquid, 1.65 MJ kilori.
Whoa, wait. It almost doubles the energy density of a Tesla battery.
As a raw material, yes. To put that in perspective, 1.6 megajoules is roughly the energy released by exploding a stick of dynamite.
You're kidding.
Or, to put it in physics terms, it's enough energy to lift a medium-sized car about 300 meters into the air.
And we are holding that in a liquid.
In a kilogram of liquid.
Yeah.
It is incredibly dense storage.
That is mind-blowing. We're talking about a liquid that beats solid-state tech.
Okay, I want to see this in action. In the paper, they describe a proof-of-concept experiment. Can you walk us through that? Because this is where it goes from theoretical chemistry to, like, a magic trick.
Right. So they took about 107 milligrams of this charged material, dissolved in a tiny bit of water.
Okay.
At the start, it's at room temperature, about 20 degrees Celsius, just a little vial of clear liquid.
Innocent enough.
Then they add the trigger. In this case, it's a tiny drop of hydrochloric acid. This acts as a catalyst. It basically breaks the lock on the mousetrap.
And what happened? The molecules snap back to their relaxed shape instantly. In less than 1 second, the temperature of that water shot up from 20 degrees C to 100 degrees C.
It boils.
It literally boiled instantly.
Well, that is straight out of a movie. You add a drop and poof, steam. But wait, if it gets that hot, that fast, does the molecule just burn up? Is it a one-time use thing?
No. And that is the crucial part. The heat wasn't generated by combustion. The molecule didn't burn. It just relaxed.
It released the tension,
It released the tension it was holding from the sunlight.
which means you can use it again.
Exactly. Once it releases the heat, it's back in state one, the relaxed pyrimidone. You just put it back in the sun, it absorbs the UV light again, snaps back into the cage shape, and it's recharged.
Infinite reuse.
They cycled it over 20 times in the lab with zero degradation. In theory, you could do this thousands of times. It's a closed loop. You aren't burning fuel, you're just borrowing a shape change.
This is fascinating because it solves that cold coffee problem on a planetary scale.
It really does.
So let's unpack the real-world impact here. Because boiling a few drops of water in a lab is cool, but why does this matter to, the listener driving to work right now?
Think about where we use energy. We talk a lot about electricity lights, computers, EVs, but nearly half of global energy demand is just for heating.
Heating homes, heating water, industrial processes.
Exactly. And right now, we mostly burn natural gas or heating oil to do that. That's a massive source of carbon emissions. We have solar panels for electricity, but if you want to heat your house at night with solar power using current tech, you have to turn sun into electricity
Store it in a battery.
and then turn it back into heat.
Which is incredibly inefficient. You lose energy at every single step.
Right. This molecule cuts out the middleman. You capture the sun as potential heat and release it as heat.
Yep.
Imagine a system on your roof. Clear tubes filled with this water-soluble mix. It circulates all day in the summer, soaking up the sun, clicking those molecules shut.
And then the charged liquid goes into a big tank in my basement.
Correct. It sits there, cold, room temperature, all summer and fall. Then December hits. A snowstorm knocks out the power lines. You have no electricity. You turn a valve, run that liquid through a filter that triggers the release, and boom, hot water for your radiators, your shower, your tea.
It's a liquid battery for heat.
That's the best way to describe it.
I love the off-grid potential, too. The paper mentions something about de-icing.
Oh, this is a brilliant application. Think about airplanes or even just your car windshield in winter. De-icing is a pain.
But hold on. I can buy a jug of de-icing fluid at the gas station for like $3. Why would I want to spray high-tech, lab-grown chemicals on my windshield? Isn't that going to be crazy expensive?
In the short term, yes, it would cost more than the blue stuff. But think about the context of aviation. Currently, they use glycol-based fluids. They're heavy, you have to use a lot of it, and it's toxic runoff.
Okay, so environmental impact is a factor.
A huge factor. But also efficiency. The current stuff works by lowering the freezing point of water chemically. This new stuff works by, well, exploding with heat. Imagine a spray bottle of this charged liquid. As it hits the surface, it instantly jumps to 100 degrees C.
So the ice doesn't just melt, it gets vaporized.
Instant melt.
Yeah.
And because the liquid is water-soluble and non-toxic, it's much safer for the environment.
I'm imagining survival kits, too. You're stuck on a mountain, you have a pouch of this liquid sun, you crack it like a glow stick, and you have instant boiling water to cook a meal or keep warm.
That is a very viable near-term use case. High-value portable heat, where plugging in a battery just isn't an option.
Okay, I am getting carried away with the sci-fi possibilities, but you are the expert here. Bring me back down to earth. What's the catch? Why can't I buy this at Home Depot tomorrow?
There are always hurdles. The first one is the light source. The paper notes that this molecule specifically absorbs UV light around 300 nanometers.
And sunlight isn't all UV.
Far from it. UV is only about 5% of the solar spectrum. So right now, this molecule is ignoring all the visible light and the infrared.
It's leaving a lot of energy on the table.
A lot. To be truly efficient for home heating, they need to tweak the molecule to absorb visible light too. The whole rainbow.
So it needs to be less picky about what light it eats. What's the second catch?
The second catch is the trigger.
Yeah.
In the experiment, remember they added a drop of hydrochloric acid.
Yeah, which sounds great for a demo, but I don't want to be pouring acid into my heating system.
Right. If you add acid, the liquid becomes acidic. You have to neutralize it before you can recharge it, or you'll corrode your pipes. You can't just keep adding acid forever.
So how do they fix that?
The authors discuss this. The goal is to move to a heterogeneous catalyst.
Unpack that word for us.
Think of it like the catalytic converter in your car, or even a Brita filter. Instead of pouring acid into the liquid, you flow the liquid over a solid surface that triggers the reaction.
Oh, I see. Like running water through a filter, but the filter makes the water boil.
Perfect analogy. If they can get that solid catalyst working efficiently, you have a completely closed loop. The liquid goes in cold, hits the filter, comes out hot, and chemically it hasn't changed at all. No waste.
That is the holy grail. It is amazing how fast this field is moving. The paper mentions this beats previous records by a huge margin. It feels like we are watching a new technology be born.
We really are. For a long time, solar thermal was the boring cousin of solar electric. But this molecular storage concept, it just changes the math. It treats heat as a currency we can bank and spend whenever we want.
I love that. Banking heat.
It connects back to that bigger picture of decarbonization. We need to stop burning things. But we love heat. This technology says you don't need fire to make heat. You just need to borrow some sunlight from last July.
Borrowing sunlight from last July. That is poetry.
It's physics, but it feels like poetry.
So to recap what we've learned today from the Deep Dive Lab. First, we have found a way to store solar energy as heat, not electricity, using a molecular mousetrap that is totally different from standard batteries.
Correct. No lithium, no rare earth metals, just organic chemistry.
Second, the whole thing was inspired by DNA sun-damaged nature's oops, but engineered by the team at UCSB and UCLA to be safe, water-soluble, and incredibly powerful.
And finally, that power is real. It holds more energy per pound than the battery in a Tesla, and it can flash boil water in a literal second.
It's cool. It's really cool science.
It's the kind of innovation that makes you optimistic. It reminds us that the solutions to our energy problems might not be bigger dams or more drilling, but smarter molecules.
Tiny little mousetraps waiting for the sun.
Exactly.
Well, I hope this deep dive warmed you up, pun intended. It is wild to think that the same UV rays I try to avoid at the beach could be heating my shower in 10 years.
Science is full of irony.
Before we wrap up, I want to leave you with a thought. We talked about heating homes and de-icing planes, but if you had a thermos of this liquid sunshine, a liquid that stays hot for 3 years until you pour it, what is the first thing you would use it for?
I'm thinking perfectly heated coffee on a ski lift.
Oh, that's a good one. I was thinking instant hot tub. Anywhere. Anytime. You're camping, you snap your fingers, hot tub.
Ambitious, I like it.
To everyone listening, thank you for stepping into the Deep Dive Lab with us. If you enjoyed this glimpse into the future, hit that subscribe button. We have plenty more mind-bending science coming your way.
Stay curious and wear sunscreen.
See you next time.